Hi, I'm Chuo-Ling from Google. Today, together with my colleague Tingbo, I'm going to talk about cross-platform ML for video conferencing with MediaPipe. A quick outline of this talk. I'm going to first discuss how cross-platform ML is important for video conferencing, and then I'll provide an introduction to MediaPipe, which is Google's framework for building cross-platform ML solutions. I will then hand it over to Tingbo to talk about how MediaPipe is used to build ML solutions in Google Meet. Video conferencing has become part of our daily life, and in particular over the last year for many of us. There have been some emerging features in video conferencing systems that greatly enhance the user experience. For instance, there is background replacement, which can be used to remove the messy bedroom behind you. There is auto zoom and crop that can be used to make sure the speaker is always front and center. There's denoising that removes the camera noise, which can be quite high with common webcams. There's also relighting that emulates a perfect lighting condition. There's also gesture recognition that can be used to augment user interaction in video conferencing. And as we know these days, the best solutions that enable these features are usually powered by ML. So we know that ML is important in today's and future video conferencing. What about cross-platform ML? In video conferencing systems, the endpoints need to be deployed onto a variety of platforms. This is because the users may want to dial in from their desktop, which can run Windows or Mac or Linux. They may also want to dial in from their Android or iOS device, or they may want to dial in just from any browser so that they don't need to install additional software. This means ML solutions in video conferencing need to work across platforms. Additionally, cloud-based ML processing can sometimes be helpful. For instance, this can be helpful if you want to perform joint processing across multiple video streams, or if you want to offload the computation from the endpoints, where the computation may be too heavy on certain mobile devices. This means you have yet another platform to cover, which is the cloud. So we want these ML solutions to be cross-platform. And more specifically, this means you want to be able to build these solutions only once, but then deploy them anywhere across different platforms. Furthermore, you want these solutions to be able to adapt to platform and device-specific capabilities. For instance, when you run these solutions on desktop, you want them to be able to utilize the desktop GPU, and when they are running on mobile, they should be able to utilize the mobile GPUs, which can have a different architecture from the desktop ones. On less capable devices, you also want the solutions to be able to automatically switch to a lighter version of the machine learning models while reusing the rest of the solution as much as possible. Such cross-platform support in machine learning solutions can be very helpful, reduce development and maintenance costs in video conferencing systems. They also help avoid feature disparity, such that users can enjoy very similar experiences regardless which platforms they choose to use. And this is where MediaPipe comes in. The MediaPipe framework is developed by Google and widely adopted in Google Research and also by many Google products. It is open source at MediaPipe.dev. So in MediaPipe open source, we offer a set of cross-platform customizable ML solutions for live and streaming media. And these solutions are available on Android, iOS, Python, JavaScript, and C++. The solutions are optimized end-to-end fully, including not just the model architecture, but also ML inference and pre- and post-processing, such that these solutions run real-time processing live camera feeds at 30 FPS on most desktop and mobile devices. Let me show you some examples of the solutions offered in MediaPipe. On the left, you can see real-time tracking of the hand landmarks in 3D. And at the top here, you can see selfie segmentation, which can be used for background replacement. And on the right, there is tracking of post landmarks. And at the bottom, there's this one solution that tracks actually over 500 different landmarks, including the post landmarks and the hand and the face landmarks. And everything here, again, runs real-time on most desktop and mobile devices. You can find more solutions at solutions.mediapipe.dev. You can also try these solutions right away within your browser using your webcam at copen.io/mediapipe. Now I'll try to provide a brief summary of the concept behind the MediaPipe framework. In MediaPipe, each of the ML solutions, as presented in the previous slide, is represented as a MediaPipe graph. So on the right here, I'm showing an example of a simple MediaPipe graph. In this particular example, the input to the graph is video frames, and these video frames go through an image transformation, which can be scaling, it can be rotation, or sometimes cropping. And the transformed images are converted into tensors and then go through machine learning model inference. The output tensors are then further decoded into a set of landmarks that can be the hand landmarks or post landmarks and so on. And then these landmarks, together with the original video input frames, are being fed into a renderer to render the final output video frames. And this is a simple example, but in practice, machine learning solutions can be more complex than this. In particular, most of the MediaPipe open source solutions actually have loops in the graph or multiple branches, or they can run and coordinate across multiple ML models. MediaPipe framework also offers language bindings to easily run these solutions in different languages to make them more accessible across different platforms. And within a MediaPipe graph, each of these nodes is implemented in C++. MediaPipe open source offers a set of built-in nodes that already cover common ML inference and post and pre-processing tasks. And moreover, these nodes usually come with multiple backend implementations. This means there's typically a standard CPU backend implementation, but there are also other implementations that utilize hardware acceleration using, for instance, OpenGL, OpenCL, or Metal on iOS, or WebGL in browsers. And the best backend is selected by the framework depending on the target platform. Aside from the built-in nodes, users can of course implement and use their own nodes. Because MediaPipe is open source, users can choose to use existing solutions in MediaPipe open source as is, or they can add their own further customization, or they can use MediaPipe as a framework to build their own solutions. So here I want to show you some examples from our MediaPipe open source community. On the left, this is a use case of remote robot control using MediaPipe. And this actually works on top of an off-the-shelf video conferencing system. The video feed of the human sender is actually being analyzed at the receiver side where the robot sits. The analysis is through MediaPipe hand tracking, and the resulting hand landmarks are further interpreted into a set of gestures which are then used to drive the motion of the robotic arm. In the middle, I'm showing an example of sign language understanding. And to my knowledge, this is not yet applied in a video conferencing setting, but you can imagine such ML solutions for sign language understanding can be very, very helpful to improve accessibility in future video conferencing. And the use case on the right is avatar. So if you look closely, you can see that this avatar is being driven by the human user vaguely seen in the background. And this runs entirely on the mobile devices. And again, you can imagine such kind of avatar-based communication can become a type of experience in future video conferencing. With that, let me hand it over to Tingbo to talk about how MediaPipe is used within Google to build ML solutions for Google Meet.
Thanks, Chuo-Ling. For next, I'm going to do a deep dive of some of work in Google Meet. Here are a list of Meet features powered by MediaPipe. We have background blur and replace, video background, light adjustment, and auto zoom. All the features are running on device and cross-platform. In this deep dive, I'll pick background features as an example. For the ML solutions of the Meet features, we have to consider cross-platform. Google Meet runs on multiple endpoints, including web and apps on Android and iOS. We choose to run machine learning on device. It's privacy conscious. The media data are processed and encrypted locally. It has low latency, as we don't need to send data to cloud for processing. Given web is the major endpoint of Google Meet, we build our solutions on device with the focus of WebML pipeline. This figure shows our WebML pipeline. Within the browser, everything runs in the sandbox environment. We compile our code to WebAssembly by mscripting. WebAssembly is a low-level language that runs in native speed on web. Mscripting provides the toolchain for compiling C++ to WebAssembly, and SIMD is a technique for data-level parallel processing. I will come to some details later. There are two types of components in this pipeline: model inference and rendering. For model inference, we have XNNPACK for CPU and WebGL for GPU. Rendering components are written in OpenGL ES shaders. They can be used for processing and rendering effects. The pipeline runs everything on the client side, directly in the browser, so it's privacy conscious with low latency. On-device machine learning has challenges of limited resource, efficient models, and cross-platform compatibility. But there are additional ones for WebML. For example, single-thread scheduling. The execution in web is a single thread shared with browser UI. For MediaPipe non-web pipelines, scheduler delegates tasks to workers in an async way. But for WebML, scheduler has to run all tasks on the main thread. As mentioned before, WebAssembly is a binary instruction format for web. It's optimized for size and speed to minimize the packet size and execute at native speed. It runs in a sandbox environment, enforcing the same origin and security policies of the browser. Mscripting is a compiler toolchain to compile code to WebAssembly, with a special focus on speed, size, and the web platform. The output is compact. and runs at near native speed. It also converts OpenGL to WebGL. SIMD refers to single instruction, multiple data. SIMD can boost performance by exploiting data level parallelism and is also useful when compiling native code to WebAssembly. For some of models, WebAssembly SIMD can boost the performance by 100%, double the FPS of CPU model inference. We use XNMPeg for CPU model inference. XNMPeg is highly optimized library of floating point neural network inference operators. It runs cross-platform, including ARM, WebAssembly, and x86. It is the first neural network library optimized for WebAssembly SIMD, and it's the first to demonstrate real-time ML inference in the browser. It powers CPU inference of ML models, including segmentation and face detection in Google Meet. The background features adopt a segmentation model to separate the person from the scene. For backbones, MobileNet v3 and EfficientNet are good candidates for on-device ML. To make the model run faster, we compress the model by searching the trade-off between quality and speed. We use LR-ASPP block from the MobileNet v3 in our decoder and build a segmentation head with channel-wise attention, which outputs the same resolution as the input. The on-device models needs to be lightweight in order to run in real time with limited resources. There's also a difference between CPU and GPU inference for model design. CPU models have to run on inputs with low resolutions to avoid large numbers of flops, which is slow for CPU inference. And GPU has better parallelism. It's more useful for high-resolution inputs. The model we built is ultra lightweight, which has only 0.2 million parameters and about 0.2 megabytes of TF-Lite FP16 file. For the base model, it has 64 million flops. In this slide, I discuss some loss functions for the segmentation task. Cross entropy is widely used for multi-class semantic segmentation. We found for two-class segmentation, the J-car loss results in better IOU metric. The J-car index is computed as intersection over union. From literature, we found there are different quantifications. The basic ones are sum and square sum. The sum quantification results in sharp edges and higher per-frame IOU, but is unstable across frames. The boundary of segmentation mask can be flaky across frames. The square sum works towards another direction. It results in soft edges, lower per-frame IOU, but more stable across frames. The problem there is it tolerates noise too much, such that the output mask is not clean. We found the mixture of the two quantifications can be stable across frames while suppressing the noise. Sparsity is one of our efforts for improving model inference. Sparsity refers to zero weights in neural networks. During training, we can drop some weights that are close to zero. The zero weights are uniformly distributed, but the structure can be enforced. so we can accelerate the model inference. Currently, only one-by-one convolutions can be sparsified. The models where the dominant operation is one-by-one convolution can be significantly boosted. Both EfficientNet and MobileNet 3 are good ones for sparsity. For more details, please refer to the reference. We apply sparsity in some of models. The left figure shows inference time over sparsity level. The inference time is reduced when increasing the sparsity level. The right figure shows model quality over sparsity level. When increasing the sparsity, at some point, the quality drop is significant. According to the measurement, we can find a good trade-off between speed gain and quality drop. In the example of segmentation, we build a sparsity model that runs 30% faster without dropping the quality. So far, we talked about CPU models. We know that GPU has better parallel processing for model inference. However, JavaScript and WebAssembly modules are executed in a sandbox virtual machine, which disallows access to native system resources. To use GPU for model inference in web, we write the inference engine by WebGL. WebGL is a JavaScript API for rendering in web browsers. Leveraging GPU, it can support machine learning models with higher capacities, measured by the number of flops. It also saves copies between GPU and CPU, which are expensive and have to be synchronized. This background replace demo shows a comparison between the best CPU model on the left and the WebGL model on the right. The WebGL model provides higher quality. Please pay attention to the arm and the hand. Both models are running in real time on devices. In this slide, I'll introduce some of our algorithms for rendering. Depends on the resolution of the output segmentation mask, a joint bilateral filter may be applied to refine the mask. In background blur, we use 1D separable filters. The algorithm is a non-uniform blur with varying kernel size and values. Usually, it's implemented by a pyramid of 2D convolutions to be efficient for computing large blurs. We instead use a different approach that compute 1D separable filters on one level. It runs faster and reduces artifacts around the person. The middle figure shows a comparison of the pyramid 2D convolutions and 1D separable filters. In background replace, we apply let wrap, which allows some light from the background bleed into the foreground. It reduces artifacts around the person, as shown in the red figure. Finally, let me briefly introduce some of efforts to scale the ML solutions to all devices. As Meet aims to provide video meetings for everyone, we need to consider a variety of devices, from high-end MacBooks to low-end Chromebooks, from Chrome that uses WebGL 2 to Safari that uses WebGL 1. The most significant component of the WebML pipeline is model inference. To ensure the model can run in real time on all devices, we provide several models adaptive to different devices. The switch between models are behind the scene according to the latency. We aim to provide users the best experience seamlessly under different conditions. If you are interested in our work, please visit MediaPipe.dev. We have more open source projects there. Thank you.